welcome to the next lecture of our blockchains course on architecture, design and use cases. We've been going through some of the details of Hyperledger Fabric and we'll be continuing to do that in this lecture. So we're going to go delve a little deeper into looking at some of the components, some of the principles, concepts in Hyperledger Fabric, how it's designed and so on. We talked about the ordering service a little bit in the previous lecture, right? So the ordering service, as I mentioned, is responsible for ordering a sequence of transactions into blocks, and it's going to deliver these sequence of totally ordered transactions to all the peers in the network. The communication with the service is via channels. So we'll talk about channels in the next slide. So there are different configuration options possible for the ordering service, and the ordering service needs to be set up before you set up the blockchain itself. Right? So the ordering service and the details of its configuration has to be included in the Genesis block of the blockchain. And there are two ordering services that are implemented today in Hyperledger Fabric. One, as I mentioned, is the Solo ordering service. It's a single node. It's meant for development purposes, and it's easy to set up, and you don't have to worry about some of the distributed, decentralized aspects of the ordering service. And this single node will just do a FIFO order. So first in, first out, whichever transactions it sees first, it will order that first. Kafka consensus is a crash fault tolerant consensus, like I mentioned in the previous lecture. And it needs at least 3 nodes at a very minimum. And we recommend an odd number of nodes in the network so that you can do a majority consensus. So that's the ordering service, and it needs to be set up before you set up anything else in the network. So the next notion is the notion of channels. And the channels, what it provides you is a notion of privacy or actually transaction privacy between different ledgers. So the same set of peer nodes, so E0, E1, can actually be part of multiple blockchain ledgers. So I can have E0, E1, E2 be part of one ledger or one blockchain. E0, E1 and E3 might be part of another blockchain, right? So these are two different chains of blocks. They can have their own, each of them can have a different ordering service if they want to. It can have the same as well. And they're all going to maintain a different scoped ledger. So each blockchain is going to maintain the same ledger. In some sense, channels, you can think of it as providing multi-tenancy. You can have different applications with a different set of peers executing on each channel. And the notion of ledgers that we talked about exist in the scope of a channel. So each channel has its own ledger, and the data in that ledger is available for the peers in that channel. So all the peers in the channel can see the data maintained by the ledger of that channel, and it's available to all so all the peers in the network have access to the entire ledger. And it's possible that channels are permissioned for a specific set of participants, like I mentioned. So you can have some subsets of the network form a channel amongst themselves to execute transactions that are private amongst them. So you can think of, let's say, a consortium of 20 banks that come together. There is a one channel that has all the 20 participants amongst themselves, but some subset of maybe 2 banks or 5 banks might come together to form a private channel that only they have knowledge of. The other nodes in the network who are not permissioned as part of that channel will not even know the existence of that channel. So that sort of privacy is possible. And the notion of channels also segregates chain code. So the chain code is the smart contract, and the chain code is installed on the peers that provide access to the world state. Right? So the installation of the chain code, think of it as you're installing a piece of software, and that is done on a peer-to-peer basis. On each peer, you will have to go and install the chain code. So a copy of the chain code is going to be running on each peer that needs to run that chain code. But chain code is instantiated for a specific channel. So for each channel here. So what we mean by this is each peer is going to be running a copy of the chain code that it needs to run. But the chain code, I can say that only channels 1 and 2. So in this example here, there are 2 channels, red and blue. E0 is part of both of these channels. E1 is part of only the red channel. So I can say this chain code is running on E0 and E1. For E0, it needs this chain code on both these channels, on both the red and the blue channel. whereas E1 needs this chain code only on the red channel because it doesn't know of the existence of the blue channel. So the chain code has to be instantiated on each channel specifically, and the state maintained by the chain code is part of the ledger, as I mentioned, and it's separate for each of the channels. So the chain code state in one channel is different from the chain code state in another channel. So these are kept private and separate. And peers can participate in multiple channels. So it's the same peer process. It's just one peer process that can be participating in multiple channels. And this becomes very useful when we are building applications for easy segregation of data and transactions across nodes in the network itself. And this also allows for concurrent execution for performance and scalability. So it's possible, like I said, let's say 20 nodes in a network. 5 of them can form a private channel amongst themselves, whereas another set of, let's say, 10 nodes can form another private channel amongst themselves. And these two channels can execute in completely parallelly with each other, and that can help improve scalability of the entire network itself. So they can all execute transactions themselves without interfering with each other. So that's the notion of channel. So we'll take a couple of examples. So here is a network with just a single channel. As before, a client application is going to submit a transaction to the network. To, let's say it contacts E0. So E0, E1, E2, E3 are the peers or the endorsing peers in this network. There is an ordering service, and there is exactly one channel in this system. So, and all the peers connect to that channel. So this is the blue channel here. So they're all represented by these blue boxes here. And this channel is going to maintain a sequence of blocks or a sequence of transactions, and that's what is represented here. Now, A and B are smart contracts. So these are chain codes that are deployed. So these chain codes are all installed on every node in the network, and they're also instantiated on that channel, right, on the blue channel. So when a transaction is submitted by the client application to the network, let's say it's invoking a particular function in smart contract A, then all the 4 peers, E0, E1, E2, E3, they're all going to be executing the same function. They all have a copy of that function. They're all going to be executing the same function across all the nodes, and then of course we'll go through ordering and consensus and then final validation. And the endorsements can also be obtained from all the. So that is a single channel network, is an example of a single channel network where all the peers are part of that single channel. Now you could also have a multi-channel network. Now there could be 2 different applications. One application is transacting on the red channel, whereas another application is transacting on the blue channel. And these applications may not even know of the existence of the other channel. If you look at the network itself, there is no way for them to even know. If they are not permitted, they won't know the existence of the other channel. Now in this example, E0 and E3 are only part of the red channel, right? And they are only aware of smart contracts that are, or chain code that are deployed on that channel. E1 and E3 are only part of the blue channel, and they don't know of existence of the red. So this is a 2 completely disjoint channels in this network. And in this example, they're actually using the same ordering service. It is possible that even the ordering service is separate across the channels if that's how you want it. But it's also possible that the same ordering service is ordering for both channels. And the ordering for the 2 channels are kept separate. So the transactions on one channel are only ordered for that channel. The transactions on the other channel are kept separate. Now the endorsement policies on these 2 channels can also be different or the same. Right? It's up to you, right? And it's on a per smart contract basis. For the smart contract Y on the red channel, I can define a particular endorsement policy. For the smart contract A on the blue channel, I can define a different endorsement policy if I choose to. It's also possible that E1, for instance, is common to both channels. So you can also have a scenario where E0, E1 and E3 are part of the red channel, E1 and E2 are part of the blue channel. So that is also possible, in which case E1 has knowledge of both the red and the blue channel. And the other important thing that I missed mentioning is the fact that even the fact that this particular chain code has been instantiated on all the nodes in the channel. So in the red channel, chain codes Y and Z have been instantiated. So that instantiation is also a transaction that is recorded on the blockchain. Not just the client invoked transaction, but the instantiation of the chain code also forms a transaction on the blockchain. So there will be a transaction that says that this particular chain code has been instantiated on this channel. So that will form a transaction in itself. So just a closer look at what the peer itself does. So like I mentioned, each peer can connect to one or more channels. These channels are completely disjoint from each other. They're private. So one channel's information is not mixed with another. And so in this case, there are three different channels. There's a blue, there's a red, and there's a green. So there are three different channels that this particular peer connects to. And each channel has its own ledger and its own blockchain, and they are all kept separate. So there is a blue ledger, a red ledger, and a green ledger. They're all kept separate. The actual process for the chain code, let's say there's chain code A and chain code B. These chain code are processes. They're run inside actually Docker containers. You can package them as just processes, or you can package them as Docker containers. So think of the chain codes as Docker containers, and those processes are running. But across all the channels, let's say chain code A and B instantiated all three channels. So let's say blue, red, and green all have a need for chain code A and chain code B. They will be instantiated three times, one in blue, one in red, one in green. But there will be only one process that is running. So that is the multi-tenancy that we support. The same process will serve transactions in the blue ledger, serve transactions in the red and the green. Right? So there's just one copy of the chain code. You could run multiple copies of the chain code if you choose to, but just one copy is sufficient. And like I said, chain codes are instantiated separately in Docker containers for each channel, but there's just one copy of the chain code running. So that's what it says here. No state is stored in the chain code container itself. It's stored in the ledger that is maintained by the peer. So there is going to be communication between the chain code and the peer, and communication between the peer and the ledger. All of these happen through remote procedure calls. So we use Google RPC, gRPC, and these are all pluggable components. So the ledger, you can plug in your own database implementation of the ledger. You can plug that in. The peer implementation can be modified. The chain code implementations are pluggable. So all of these components are pluggable in nature. Today, the peer is written in Golang. It's a new upcoming language for distributed processing. So all of these components, the peer, ledger, are implemented in Golang, and they communicate via gRPC. So any language that gRPC supports can be supported. So tomorrow you could potentially write the peer in Java if you choose to. It's possible. The chain codes, there are multiple languages we support the chain code to be written in. So we support Golang chain code, that is the most popular that we have seen. We also support Java as well as JavaScript chain code. So those are also available today for application developers to use. Another important notion of the peer itself, just made a fleeting reference to it before. The peer itself has an identity. Right? So it has a certificate that is issued by a recognized certificate authority on the network, and the peer has a PK infrastructure. It has a public key and a private key, and it is going to use those keys when it is communicating with other peers in the network, or with the ordering service, or with client applications. Events emitted by the peer are all signed by the certificate that the peer has. And the membership service provider, we'll have actually a lecture talking about what the membership service provider does. It provides the crypto material that the peer will use to authenticate users transacting on the blockchain. There will be there's a notion of organization, there's a notion of a user within an organization. So the crypto material for authenticating and validating these users on the blockchain will be available to the peer using a local membership service provider that it maintains. There's also a notion of global membership service provider, but we'll talk about that later. So that's the overall function of what the peer does. Now coming to the client application, I think we talked about this. It's possible for one client application to work with multiple channels, just like before. So these are all kept separate. They have to work with the particular peers on those channels. And it can also receive events from multiple channels. And the SDK needs to be connected to, again, a local membership service provider that has the crypto material for the users using that application. Based on the channels, the client might also have to communicate with one or more ordering services. So the blue and red might be using one ordering service, green might be using another ordering service. So the client application has to be aware of the ordering services. And all this information is available in the Genesis block, like I mentioned. So who are the peers in the channel, who are the ordering service, what is the ordering service, all of that information is available to the client application in the Genesis block. And the peers in the channel can also be dynamic. So it's possible that one peer leaves the channel at some point during the course of execution. Maybe after the first 100 blocks, one peer leaves, and there might be another peer or another organization that joins the network. And they can then join the network from block 100, but they can get the history of all the previous blocks that they missed. So peers can enter and leave channels dynamically. And the fact that the way peers entering and leaving the channel are also recorded as transactions on the blockchain. So they are called channel configuration transactions, and they are also recorded on the blockchain, again in a decentralized manner. So everyone has to agree that this peer is now okay to join this channel, and they will be admitted into the channel. And when a peer is admitted into the channel, of course, the crypto material for that peer has to be updated. And the client, the application itself can be written in any language, but the client that connects with the blockchain, there are multiple SDKs that we provide. We provide SDK in Node.js, Java, and Python, and you can use that to connect with the blockchain. So a little bit on the Fabric Certificate Authority. So like I mentioned, this is one implementation of a certificate authority that issues identities for users or components transacting on the blockchain. So this could be for users, for peers, for ordering service nodes. All of them have identities on the blockchain. And the Fabric CA can be used to issue all of those identities. So there are many ways in which you can implement the certificate authority. One implementation is provided today. There is one more called IDE Mixer, which is also getting implemented. We might talk about it in advanced lectures later in the course on security and privacy. So the Fabric CA is attached to a root certificate authority, and it can have multiple hierarchical levels. So you can have intermediate certificate authorities that link to the root CA and so on. It has a database for high availability, and it can also support high availability characteristics. So even if, let's say, one part goes down, it'll still be functional. It can be connected to other identity mechanisms like LDAP and so on. And the keys that are issued by the Fabric CA are stored securely in a hardware service module. Right? Now, what do the identities themselves look like? So there is notion of an enrollment certificate. The enrollment certificate defines your identity on the blockchain, and it's called your long-term identity. So we'll talk about some of the notions of identity and how identity is used in the blockchain itself in one of the subsequent lectures. With that, we are coming to the end of the lecture itself. So again, some fun reading for you to gather some of the concepts we've introduced here, to learn more about some of these concepts. So if you're not familiar with what a certificate authority is, I would encourage you to read the Wikipedia article. It's actually a well-written article. You can gain a lot of knowledge about how the world works today using certificates. So that's a good article to read. I will encourage you to read that. The architecture of Fabric itself, a detailed note of that is available online. So there's architecture deep dive page, so you can go read up in detail about the Fabric architecture. And the Fabric CA itself, how it's architected and some of the functionalities it provides is also available in the documentation. So I would encourage you all to read that as well. So hope you got a good understanding of some of the components and components of Hyperledger Fabric and how it's architected. So we look at some additional notions in the subsequent lectures. Okay, thank you.